In this video, we are going to talk about power calculations for the difference of means. This is our overview slide, which we'll spend 5 minutes or less going over before we go over our main topics with more detail and more examples. Collecting enough data to detect important effects sometimes competes with the fact that collecting data can be expensive. We want to strategize a proper sample size. We want to know how likely we are to detect an effect we care about. If there is a real effect, and that effect is large enough that it has practical value, power is the probability that we detect the effect. We compute power for different sample sizes or for different effect sizes. This is the example we will be using to illustrate. And the example is, if the company researchers care about finding any effect on blood pressure that is 3 millimeter Hg or larger, then 3 millimeter Hg is the effect size of interest, and we want to know how likely we are to detect the size of an effect in this study. So we do this power calculation. And in the example, we will find that if we have a sample size of 100 in each group, we can only detect an effect of the size 3 millimeter Hg with a probability of about 42%. Maybe the researchers will miss a real and meaningful difference that they cannot detect with such a small sample. So we calculate power for several different sample sizes to determine the appropriate sample size. And even better, we will see an example where we have a computer calculate power for several different sample sizes. And when we graph that, we will see there's often a sweet spot for sample sizes. So that concludes our overview. So let's go back over this and look at the concepts in more detail and with examples. A pharmaceutical company is preparing for a clinical trial to test a new drug's effectiveness in lowering blood pressure. They recruit people who are taking a standard blood pressure medication. The people in the control group will continue to take the current medication through a generic-looking pill to ensure blinding. And then, of course, the treatment group will take this new drug. First, let's write down the hypothesis for a two-sided hypothesis test in this context. And the null hypothesis is always the one that kind of says nothing interesting has happened. Or you could say it's kind of the cautious one, that you don't want to just rush out or conclude a new drug is effective because a couple of people seem to get better. You want to be very cautious when introducing new drugs. So generally, H0 is going to be that the mean blood pressure of the treatment group and the mean blood pressure of the control group are equal. In other words, the mean of the treatment minus mean of control is equal to 0. There's no difference in blood pressure. That means the alternative hypothesis means the mean of the treatment minus the mean of the control is not equal to 0. And here this is two-sided hypothesis, so it means that the mean of the treatment minus mean of control is either greater than 0 or less than 0. We are given additional information. Researchers run the trial on patients with systolic blood pressure between 140 and 180. Previous studies show the standard deviation to be about 12. Maybe these are supposed to be lowercase letters. The distribution of the patient blood pressure will be approximately symmetric. We had 100 patients per group. What would be the approximate standard error for the mean of the sample treatment minus mean of the sample control group? We use our standard error from difference of means. We had reviewed that I guess in the last video we did. So we're going to do the standard deviation squared of the treatment group over the sample size of the treatment plus standard deviation of the control group over the sample size of the control group, all square rooted. So somewhere we have all this. Here's the standard deviation, about 12. So 12 squared over, and we had 100 patients per group, plus, again, this 12 squared over 100 square rooted, so we get 1.70 for the standard error. What does the sample mean of the treatment group minus sample mean of the control group look like? From our last video, we learned when we looked at the difference of mean, we would use the t-distribution. So we need to look at our degrees of freedom. In this case, the degrees of freedom is the minimum of the first sample size minus 1, so that's 100 minus 1, and the second sample size, which is also 100 minus 1. So the degrees of freedom is equal to 99. The other thing we talked about when we talked about the t-distribution is as the degrees of freedom increases, the t-distribution becomes more and more like the normal curve. Since the degrees of freedom is greater than 30, and as degrees of freedom approaches infinity, the t-distribution approaches the normal curve, then the null distribution for our sample mean of the treatment minus the sample mean of the control group is going to look approximately normal, as I have drawn here. I deleted a few things and moved things around to give myself space. Here's my standard error. Here's my degrees of freedom. I have a null distribution. And first we need to determine for what values of the sample mean treatment group minus sample mean control group would we reject the null hypothesis. And so for alpha equals 5%, we reject the null hypothesis is the difference in the lower 2.5 or upper 2.5. Remember, for alpha equals 5, that means we're wanting 95% of our data surrounding our mean, which means we have 5% on the two tails. So 2.5 in the lower tail, 2.5 in the upper tail. You can use the t-distribution test, but since this approaches normal because the degrees of freedom is greater than 30, the z-score associated with the 95% area around the mean and 2.5 at each tail is 1.96. You can look it up on the normal curve. So 1.96 standard errors, and the standard error is 1.7, is 3.332, whatever this pressure measurement is. So we will reject H0 if blood pressure difference is greater than 3.332 or less than negative 3.332. So again, I kind of summarized this over here for our 5%. This is where we reject. So if the company researchers care about finding any effect on blood pressure that is 3 millimeter Hg or larger, then this 3 millimeter Hg is the effect size of interest, and we want to know how likely we are to detect the size of an effect in the study. This is where we're going to start talking about power, but keep in mind how we did this hypothesis testing here based on our H0, where there's no difference, because this the power calculations are very similar. I have moved up our summary of the hypothesis testing here for our reference, and let's just quickly review. So we looked at the difference between the mean, and our null hypothesis says the difference is going to be 0. We calculated our standard error. We calculated the degrees of freedom. Then for a 95% confidence interval, we figured out what the z-score should be. So the z-score was 1.96 for a 95% confidence interval. And then from there, we figured, well, how many units is 1.96 standard errors? We multiply our 1.96 times our standard errors, and we say, okay, then we're talking about a 3.332 number of units that are going to be either bigger than our difference between the means or smaller. So it's 0 plus or minus 3.332. Now, for our power calculation, what we want to know is the probability of finding any effect on blood pressure that is 3 mmHg or larger. So now 3 mmHg is the effect size of interest. So now we're going to say our sample, the difference between the treatment and control group, then we want to know if it's 3 mmHg or larger. And at this point, kind of our new working hypothesis is going to be, again, remember the treatment, because this is a blood pressure medication that lowers your blood pressure. So we're hoping that the treatment is less than control, which is why we have this -3. So again, our new kind of working hypothesis is the treatment minus the control on average is going to be -3 mmHg. Again, treatment smaller than control. I'm going to kind of notate this as kind of our new working hypothesis, that our treatment minus control is less than or equal to -3, and I get that here. But the thing is the sampling distribution has the same characteristics that we had before. It's the normal distribution. The only difference is now, because our working hypothesis is that the true difference is -3, is that our null distribution shifts over 3 units, so that its center is at -3. So this is the new kind of norm or normal curve that we're going to be working with, and we can do all of these calculations again. So let's see what calculations need to be redone. Coming over here, our standard error was dependent on standard deviation and sample size, so those things have not changed. Our standard error stays the same. Our degrees of freedom depends on sample size. We haven't taken a new sample, so that's going to stay the same. So for a z-score associated with a 95% confidence interval around the mean, that z-score is still 196 times standard error, and that gives us the units, 3.332 units above or below the mean. So at this point over here, we're talking about, over here we have some measurement that's 3.332 units. These are not standard, let's see. These are not standard units, right? Because these are actual units. The number of standard units it was 1.96, or standard errors. So over here in actual units, 3.3392, and that's negative. And we want to calculate the probability that x is less than this 3.332 for a normal distribution with mean of -3, again our new distribution shifted over, and standard deviation stays the same, 1.7, or standard error stayed the same, 1.7. Basically we're estimating our standard deviation with the standard error over here. And the area we want to calculate then is shaded in green, anything less than or equal to minus 3.332. So this is our new kind of problem we're working with. Here's our normal curve, here's the measurement we want. So now we need to know how many standard units is minus 3.332 relative to the mean. In other words, we need to get the z-score now for this, but not relative to our 0 mean, but relative to our -3 mean. So the z-score we're going to be looking up when we look at the tables is our minus 3.332 minus our mean, which is -3, divided by standard error, 1.7, which is -0.2. We can look this up on our table for the normal curve. So now I need to look this up on my normal table. I have one for the positive z-scores, not for the negative that I have here, but that's okay because we can work around that. Let's look up the area for the positive z equals 0.2. On my normal table, I have 0.20, so it's 5793. That's this blue shaded region, 57.93%, or 0.5793. Since the total area under the curve is equal to 100, that means this part over here that I'm just going to put in green is 100 minus 57.93, and that's going to give me 42.07%. By symmetry, because this is a normal curve, that means the z-score here from z equals -0.2, this should equal this. So what I finally get is my area is equal to approximately 42%. So what we're saying here, our original hypothesis, which was the difference between the two, that the one treatment was no better than the other, that there was no difference, we would tend not to reject the null hypothesis anytime we're within this region. But if the actual difference is there, if there really is a difference, 3 mmHg, which is over here, our -3 mmHg, 42% of the time we will manage to reject H0 and say, yes, there may be a real difference. But that also means, what, 58% of the time we're saying there's no real difference when there really is. There's this 3 mmHg difference. To summarize now, also using our new vocabulary, the power for the test is about 42% when the difference between the means and the population is really -3, and each group has a sample size of 100. So in this example, we found that if we have a sample size of 100 in each group, we can only detect an effect size of 3 mmHg with probability about 42%. So we miss it about 58%. Maybe the researchers will miss a real and meaningful difference that they cannot detect with such a small sample size. Now we're going to redo the same example, but change the sample size to 500 to calculate the power. So previous studies has shown the standard deviation will be about 12 mmHg, and the company's researchers care about finding any effect on blood pressure that is 3 mmHg or larger. And again, 3 mmHg is our effect size. We have our null hypothesis says there's no difference in blood pressure. In other words, the treatment really has no advantage over the traditional treatment that we currently have. Our standard deviation, 12 mmHg, is the same. However, our standard error is going to change because our sample size has changed. So our standard error is going to go down to 0.76. Again, for our significance level of 5%, that means our z-score is going to be associated with 1.96. So now we need to recalculate this number here using our new standard error. So a z-score of 1.96 times our new standard error, 0.76. So we're talking about 1.49 units away from the mean. So 0 plus or minus 1.49. So we're going to reject our hypothesis if it's outside this window of negative 1.49 and 1.49. Again, we're going to use this new working hypothesis, our effect size, which is going to shift our normal curve from a center of 0, a difference between the means of 0, to a difference between the means of negative 3. Negative because we're guessing that the treatment gives you a lower blood pressure than control. Now this number, 1.49, is much smaller than we had before because when we multiply our standard errors by 1.96, the standard error calculation gives us a smaller value here. So now our value for x bar here is going to be negative 1.49. And so now we need to calculate the probability that x is less than 1.49 for a normal distribution with a mean of negative 3 and standard deviation or standard error of 0.76. The z-score then is our negative 1.49 minus our mean, which is negative 3, divided by standard error. So our z-score for this negative 1.49 point is 1.99. On my table, I see with 1.99, I capture 97.7% of our data. So with n equals 500, we would be about 97.7% sure to detect any effects of at least 3 mmHg in size, which is a substantial improvement from the 42% we had worked on previously when we were using a sample size of 100. We're going to use the same example, and we want to know what size will lead to a power of 80% with the 5% significance level. And again, we have our 12 mmHg as our standard deviation. We care about 3 mmHg for the effect size. We have our null hypothesis here. Looking at our normal distribution table, if we want 80% of our data lower than our z-score for positive z-scores, we're talking about 80%, something in here, so something between 0.84 and 0.85, right? Because this is 0.8, and then we're between 0.4 and 0.5. We are going to use z equals 0.84. And for 5% significance level, or p-value, we want our z-score to be 1.96. So when you look up z equals 1.96, you'll see that 97.5% of the data is lower than that, meaning 2.5 is higher than the z-score. By symmetry, that means 2.5% is lower than the z-score, which leaves us 95% right in the middle, centered about the mean. So for our 5% significance level, we failed to reject the null hypothesis when we're within 1.96 standard errors, or our z-score is 1.96 from this mean here. But now, because we have this new distribution, we're extending this over now by our z-score on our new distribution of 0.84. So for our new distribution, we have from the mean 0.84. So this now is the extension. how far we're going to extend our do not reject, H naught. So the distance between the center of the null and the alternative distribution center is our 0.84 standard errors that we got here from our new distribution, our kind of working hypothesis, and our 1.96 from our normal distribution using our 5% significance level. So now we can use our formula for standard error, because that's the one that involves size of sample size. We have our 3 mmHg is equal to 2.8 standard errors, which is 2.8 times square root of 12 squared, that's our standard deviation, divided by n plus 12 squared over n. We solve, and that gives us n of 250.88. So our sample size needs to be 251 samples per group. We're going to do one more calculation like this, but now we're going to look at a power of 90% with a 1% significance. Again, we have our 12 standard deviation, our 3 mmHg effect size, and our null hypothesis. There's no difference in blood pressure. So we want a power of 90%. So we want in the lower tail 90% of our data. We look up our z-score, and that's 1.28. For our significance level of 1%, that means 99% of our data surrounding our mean leaves us 0.5% in the upper tail and 0.5% in the lower tail. So the z-score associated with 99.5 is 2.58. Remember, we have to look up the 99.5 since our table is giving us the area below our z-score. So looking at our graph now, for our significance level, right, this graph here is about the power. I probably should say this. For the z-score, we're talking about the power of 90%. This graph here is our significance level for our normal hypothesis testing associated with H naught. So with our normal hypothesis testing, we have this z-score of 2.58. So we're 2.58 standard errors from the mean. But now that we're doing our power, we're going to extend where we do not reject H naught by another 1.28 standard errors. So we add the 1.28 standard errors to our 2.58 standard errors, and we get 3.86 standard errors. This is going to be our do not reject range. So we plug into our formula, our 3 mmHg, our effect size is equal to 3.68 times standard error. Here's our standard error formula, our 12 squared over n plus 12 squared over n. And then from here, you can solve for n algebraically. You can calculate and plot power for several different sample sizes. And here's one plot. It's even better if you can get a computer program to do this for you. But what is interesting about this plot is at some point, somewhere over here, which is, I guess, a little over 250, you can keep increasing your sample size up to 5,000, but you're not, you're already close to 100% here, or your powers, yeah. So, there's not a lot of point in doing a sample size greater than, I would say, 300 even. Also, you can see you're kind of rising slowly, but you kind of take this inflection point. So somewhere over here around 150 is where you start to make the most gains, and then you kind of level off when you have another inflection point somewhere over here at 250. So I would say the sweet spot is somewhere between 150 and 250. But again, depending on what your needs are, you can kind of plot a few of these, have a computer program do it for you, and then choose what a good sample size would be. In this video, we talked about the power calculations, and the idea is collecting enough data to detect important effects sometimes competes with the fact that collecting data can be expensive, so we want a good strategy to determine a proper sample size. So when we plan a study, we want to know how likely we are to detect an effect we care about. If there's a real effect, and if that effect is large enough that it has practical value, power is the probability that we can detect the effect. We compute power for different sample sizes or for different effect sizes. And we went through this example here, and we found if we have a sample size of 100 in each group, we can only detect an effect size of 3 mmHg with probability of about 42%, meaning that this effect, even if there is a significant effect, we only detect it 42% of the time, meaning we miss it 58% of the time. So maybe we'll miss a real and meaningful difference. And so what we look at is changing the sample size to decrease our standard error and kind of give us a better power. So we can calculate power for several different sample sizes, and as I showed in the last graph, often there's kind of a sweet spot of where the sample size should be. So that's it for this video. Thank you for watching.